In this video, I want to outline the predicates that we would need to prove correct in order to show this code segment correct. This is the code segment that uses the Euclidean algorithm to find the greatest common divisor of two non-negative integer inputs. So, notice that the code segment involves a loop. So we know there's an invariant. The precondition is that we input two integer values that are both positive, and the invariant is that the GCD of these inputted values is the GCD of some updated values found in the variables x and y, but both x and y are positive and are both less than or equal to the inputted variables. So we know that because if this is true, this invariant holds before we start the loop. If it's true and we do an iteration, which means at the top the invariant holds and the guard holds, that after we perform the command, we will end up in a state satisfying the invariant again. And when we exit the loop, which means that the guard does not hold, but still the invariant holds, that's supposed to imply the post condition of the entire program segment. So let's list out the predicates that means we need to prove. Well, since there is no command before we enter the loop, that means that the precondition must imply that the invariant holds. So that's the first thing we would need to prove. Then we would need to prove that if the invariant holds and the guard holds, so we do perform an iteration, then we perform the command and end up in a state satisfying the invariant again. Then we need to show that if the invariant holds but the guard does not, we exit the loop, and that should leave us in a state satisfying the post condition R. Now, these show partial correctness. If I want to show total correctness, I need to show that the loop terminates. So in order to do that, I need to find a bound function t, which satisfies that while we're iterating, which means the invariant holds and the guard for the loop holds, that this bound function always takes on values that are bounded below by 0. And when we iterate, which means the invariant holds and the guard holds, if we made a copy of the bound function value and then we performed the command in the loop, we should end up in a state where the copy is greater than the updated. So this bound function decreases every iteration, which means it must have terminated. So we would need to figure out t. What is t, this bound function? Notice for these conditions to hold, it has to be a function of the variables that are being updated in the loop. X and y could be updated. Well, if this guard holds x less than y, then y is updated but x stays the same. Otherwise, x is updated and y stays the same. So this function, bound function t, can't just be a function of x or y alone. it has to be a function of both of them to ensure that every iteration it decreases. So I'm going to set t to be equal to x plus y. Notice x plus y are both supposed to be positive. Well, x and y are both positive, so x plus y has to be greater than or equal to 0. And while one of the variables stays the same, the other decreases every iteration, so this function will be decreasing every iteration. So I think that this is the bound function that will work. We'll have to prove it, but I'll save that for a later video. Notice I left some space here. The reason I left some space here is because the command inside of our loop is an if command. And typically what we would do in order to prove a triple correct is we would show that the precondition implies the weakest precondition of the command postcondition. In this particular case, though, for an if, that weakest precondition is long and could be cumbersome, so we decided to use the if theorem. Recall, the if theorem would tell us if we had a if command with two guards, in order to prove it correct, we would need to show that the precondition for the if implies at least one of the guards holds, and then for each one of the guards we would need to show that the precondition and the guard implies the weakest precondition of the command corresponding to the guard, the postcondition. Well, let's see what that looks like for this particular case. Notice the command is an if, but the precondition for that if is that the invariant and the guard of the loop hold. So we would need to show that the invariant and the guard of the loop implies at least one guard for the if must hold. Then we would need to show for each one of the guards that the invariant and the guard, since that's the precondition for the if, and let's say the first guard implies the weakest precondition of the command corresponding to the first guard, y becoming y minus x, leading us into a state satisfying the postcondition for the if. But notice the postcondition for the if was the invariant. We would also need to show that the invariant and the guard for the loop and the second guard for the if implies the weakest precondition of the command corresponding to the second guard, where the postcondition is the invariant again. So there are, let's see, 5, 6, 7 different predicates that we would need to show hold in order to prove that this program segment is correct. And we'll do that in future videos.